This speaker who is my colleague Boris Svistunov. So Boris got his PhD in Moscow, in Kurchatov Institute, under the supervision of Yuri Kagan, so that makes him third.
And I had to
yes, that's true. So Jura didn't show up, only talk.
Then by supervision of Yuri Kagan.
So that makes Boris like third generation Landau descendant. So Kagan was a first generation Landau. Second. Boris was professor at UMass Amherst since 2003.
So, thanks for the introduction, and let me also thank the organizers for having me here. I really enjoy it. Actually, it's my last day, so for me it's almost over. And I will tell you about superfluid turbulence. So it's not my mainstream as first principles. Methods of quantum statistics, but somehow I was always interested in this stuff. I started doing it in '95. I got involved into this business just through my interest in ethics of Bose-Einstein condensation, which I was developing at the time, which naturally leads to superfluid turbulence. That I will explain a little bit later. And sometime after, Evgeny Kozik joined me as a student in Russia, at Kurchatov Institute. That he came with me to UMass, and basically we were continuing working on these interesting topics. And recently, during recent years, this topic became very hot because of the experiment at very low temperatures. Actually, the experiment with superfluid turbulence, the first experiments by Weiden, just famous experiments, were done before I was born. But at that time, and it was just typical to create superfluid turbulence by counterflow. Counterflow is when you have a heater, a reservoir with helium, and normal component goes from the heater to the reservoir. Superfluid goes from reservoir to the heater, and if the velocity becomes larger than the critical one, this stuff creates superfluid turbulence, which is a tangle of vortices. And only relatively recently, I would say since '95, but it was just my paper, and I would say the real interest of the community, of the superfluid community to this topic, the superfluid turbulence at zero temperature, began only in the year 2000. So it is just one decade of intensive study with very important result. They is pretty recent. So what is superfluid turbulence? A superfluid cannot rotate, as we all know, but it can mimic rotation by having vortex lines. So a superfluid turbulence is a tangle of quantized vortices. And actually, there can be two distinctly different types of superfluid turbulence. When the tangle is chaotic, or when the tangle is polarized, at least locally. If you have a tangle like that, then a superfluid can mimic the motion of an ideal, if we are talking of zero temperature, and I will be mostly talking of zero temperature. This is the most non-trivial case. Then the fluid can mimic a macroscopic motion at large scales of just ordinary ideal fluid, and at the macroscopic scale you see no difference. Here the story.
So I'm just confused. I mean, isn't that a matter of length scales? I mean, it could look like one on the short length scale and the other
right,
on the long
normally, but normally what you observe, say if you are talking of the Kolmogorov cascade, what you observe is the main scale. Remember, it's just the essence of cascade. The time scale is given by the main, by the largest correlation length, normally the system size. And basically something happens, energy disappears at shorter wavelength. But if you do not have a probe sensitive to the short length scales, dynamically you just see some characteristic time which will be exactly the same in an ideal fluid and in a superfluid. That's the point. But what I will be talking about, just about the question you asked, do we see something at shorter scales? Exactly, we do see something, and we see something very dramatic at shorter scale, but we need a probe sensitive to this shorter scale. Just Yegor was introducing me, saying that I was doing my PhD by the supervision of Kagan and Kagan, and I just mentioned your name.
Thank you very much for mentioning mine.
But somehow we didn't see you, so very good. So that's basically the setup. And if you ask me what is a chaotic tangle, the answer will be, this is a delicate question, because naively we can say we just draw something randomly, and that's what people normally do when they simulate what they believe to be a random tangle. But the point is that if we are talking about superfluid, normally by random we mean the absence of correlations in terms of the phase of our complex value for the parameter. And it turns out that the absence of correlations in terms of the phase actually means some extra correlation in the tangle which we call a random tangle. You can easily figure it out if you will consider just a two-dimensional case, and if you randomly drop pluses and minuses, vortices and anti-vortices, and you will see that if you drop them randomly, you create some fluctuations which would be reminiscent of this picture. So really randomly means, because remember that vortices, they interact like Coulomb particles, meaning that actually long-range correlations, fluctuation actually are suppressed. And if we really say want experimentally to create a really random tangle, we can start with kinetics of Bose-Einstein condensation, which in essence can be described by Gross-Kitaevsky equation with random initial condition. You take harmonics just with random phases, and that's what we did with Natalia Berloff in 2002, and these are the results of our simulations. And then the system evolves, and as a result of this evolution, out of this absolutely structureless picture, when you do have lines with zero density, you can call them vortices, but they are not individual degrees of freedom. Good individual degrees of freedom here are just Fourier harmonics. And then, step by step, you arrive at this state when you have well-defined vortex cores, and that's what actually we should mean by an absolutely random tangle. And it's interesting that recently this scenario was observed experimentally by the group of Brian Anderson. Basically, their end point, they ended up with stuff like that in a torus. And if you have a torus, toroidal geometry, you end up with a super current, with persistent current. So their observation was that after doing this strongly non-equilibrium Bose-Einstein condensation, you can end up with a supercurrent state rather than just.
Did they have a toroidal geometry?
Yes. That's what I mentioned. By the way, feel free to interrupt me anytime if you want to clarify something. But my most interest will be in polarized tangles in the superfluid turbulence, which behaves classically at large scales. The first experiments were done quite some years ago, but the first experiments were at essentially finite temperature. Then, and basically what people were observing, that a superfluid turbulence was behaving classically like Kolmogorov cascade, and I would say this is the most non-trivial situation at finite temperature, because at finite temperature we have a two-component fluid. So as opposed to zero temperature where fluid is single component, we have something extra in addition to the classical fluid, which is single component. But still, this normal component was coupled to the superfluid bar, and the whole thing was behaving like an ideal fluid.
But what were they measuring?
Uh,
What were they actually doing?
Let's say relaxation time, the spectrum, the energy spectrum. The simplest quantity which you can measure is the relaxation time, how velocity relaxes at the main scale.
Okay, but you need to also measure not just time, but also spatial relations.
Oh, it's more than trivial. It's more than trivial. But the relaxation time is the easiest because you see how your energy dissipates.
But dissipation happens because of normal component?
No, because of Kolmogorov cascade. Because Kolmogorov cascade, you see, an ideal fluid, an ideal classical fluid is dissipative on its own because of the vorticity. Helium is superfluid only because vorticity is quantized. If vorticity is not quantized, you have dissipation due to the turbulence. Turbulence is dissipative on its own.
But turbulence itself cannot dissipate, it only transfer energy somewhere else.
Right, right. So it transfers energy to shorter and shorter length scales.
So you just say that it keeps...
You observe the main scale, like the system says. You observe what's your macroscopic flow at the length scale, which is essentially the size of your system. You see, you observe the macroscopic flow, and you see that basically you do the averaging of distances that are on the order of the system. And you see how your typical velocity gets smaller and smaller. It's the essence of Kolmogorov.
You don't worry where the energy goes, you just say that...
I do, but just experimentally, it's not easy to address this question. And basically, on the next slide, you will see how experimentalists can address this question, just on the next slide. Okay? But before I go to the next slide, I really want to mention this simulation. So yesterday, I was mentioning this simulation to Masahid, especially for you. So in 97, there was a simulation of Gross-Pitayevsky equation with such an initial state which would mimic the macroscopic flow of an ideal liquid. And they, no wonder, for some reason, people just were really excited about this work, but for me it was something very natural because it was known since Feynman that actually a superfluid at zero temperature can perfectly mimic at large scales the flow of an ideal liquid. Anyways, this is a direct observation, and since then some experiments were done, and I just want to mention two of them, especially this one done in the group by Andrei Golov in Manchester. So they had a rotating cryostat. So cryostat was rotating, and then they were doing abrupt spin down. They just stopped their cryostat. And this is a kind of artistic picture of what's going on. So see, experimenters were drawing absolutely chaotic tangle, and actually this tangle should be polarized, but at least it's the idea of what's going on. When they abruptly stop rotation, the system behaves classically at large scales, and it just it deforms this array of vortices, which was created by rotation, and form Kolmogorov turbulence. Now, the idea of this experiment is to have something more than just the distribution of velocities at the main scale. Just to have some access to the scales which are much smaller than the scale than the size of the system. And what they were doing, they were measuring the total length of the vortex lines. Meaning that if something interesting is happening with the vortex lines at some shorter distances, they were supposed to see the difference in the total line length. And they were probing this total line length with ions. Those are the ions. Yet another experiment was done in Matti Kruse's group in Helsinki, but this experiment, it's a very elegant experiment, but in terms of interpretation, it's trickier. And I would say that at the moment, there is no well-controlled theory of what's going on, but qualitatively, it's understandable. It's pretty close to what was going on in the previous experiment. So what do? They also have a rotating cryostat with helium with helium-3 in the metastable state. So it's helium-3b, meaning that it's also U1 superfluid. They're rotated, but they do not have the vortex array. The state is metastable. It would love to create a vortex array, but you need just to spark the process. And there are two ways of doing that, and let's just discuss one of them. Here is a little orifice. They just nucleate, just do something. Frankly, I forgot what do they do specifically, but as a result, they nucleate vorticity at the bottom of the cryostat, and then they see how this rotation, how this vortex array propagates. And here, just the boundary between the non-rotating part and rotating part is turbulent if temperature is low enough. And this is the result of first principles simulations. Unfortunately, simulations cannot go to very low temperatures because they cannot trace just very different length scales, but at larger length scales they're pretty consistent. So these are simulations. They're pretty consistent with the observation. So the bottom line of these two experiments is that somehow at the same initial conditions, the line length significantly increases with decreasing temperature. Somehow, and the increase can be by almost an order of magnitude. Somehow there are more line length, while macroscopically the behavior is the same. That's basically the main circumstance which I want to understand.
Can you explain how did they measure the length of the vortices?
So the turbulence can absorb ions, and the cross section for the absorption of an ion is proportional to the total length. It's very simple. So basically, my main object of interest will be these Richardson-Kolmogorov cascade at zero temperature, which we do understand at larger scales. It's not different, as I was explaining, it's not different from the macroscopic motion of an ideal fluid. But we really want to understand what will be happening when we will be going to length scales at which we will be sensitive to the discreteness of the temperature. Namely, we can say that the relevant scale is the interline separation, and later on we will see that it's almost the case, but the situation is much more delicate. Okay. Then you can ask me a question: what will be happening if we go actually to the scales much smaller than the interline separation, to the scales which, when we have a picture absolutely different from an ideal fluid? And let me tell you right away that at the scales much smaller than the interline separation, the cascade will change dramatically. Instead of a Richardson-Kolmogorov cascade, which corresponds to the ideal fluid, we will have so-called Kelvin wave cascade. A Kelvin wave is a distortion wave on a vortex line. A little bit later I will just provide you with more details. But at this point, it's important just to keep in mind that Kelvin waves are just some distortion waves propagating along the vortex lines. And my point will be that the most important inertial range for the energy transfer will be associated with so-called pure Kelvin wave cascade. Pure means just no rings, nothing, just non-linearity of Kelvin waves, which is responsible for the cascade. And this cascade will be taking, at zero temperature, this cascade will be taking energy to such a scale at which radiation of sound will become important. So at zero temperature, the cascade, the Kelvin wave cascade, ends up with radiating of photons. This idea was formulated by Joe Weiner. And also, and probably most interesting question will be what lies between Richardson-Kolmogorov and Kelvin wave cascade. Because naively we can think, okay, but it's just a crossover, some scale at which we have a crossover, nothing interesting. The point will be that actually this crossover will take at least 1 decade of wavelength, because the crossover will turn out to be essentially non-trivial, and it will take actually a few steps before we will end up with this pure Kelvin wave cascade. Maybe it will be just the most important result in terms of this theory of quantum turbulence of Richardson-Kolmogorov regime of quantum turbulence. Okay, so, but we will start with the most simple case of a random tangle. With a random tangle, the life will be easier, and we will just introduce all the important notion discussing a random tangle. So here are some large and small parameters which are crucial for the physics at zero temperature. First of all, we have a ratio of typical curvature radius, which is also just the interline separation, if we are talking of the random tangle, over the Killing length, which is the 4 radius. So normally this ratio is very large, but it turns out that the parameter which controls some important property, which is called local induction, is only the log of this quantity, meaning that at best this parameter is order 10 of helium, and say in Bose-Einstein condensates it's order unity. So we don't have this clear-cut local induction picture in Bose-Einstein condensate. So what's local induction picture? It's basically the approximation, which is quite good in helium, or at least for a single line, in which the velocity of a vortex arc at a point R is given just by the curvature of this arc. And this approximation is controlled by this parameter. For example, if you have a vortex ring, the velocity of this ring is just given by the radius, and it doesn't really matter whether it's a perfect ring or just an arc with a given curvature radius. Locally, the velocity will be just given by the curvature radius. So-called local induction approximation, which we'll discuss later. Finally, then, in terms of the pure Kelvin wave cascade, it's important to have a parameter which guarantees that nonlinearity is weak. This is a purely geometric parameter. It's the ratio of the amplitude of the distortion to the wavelength. So the amplitude is measured in the units of length, and the wavelength in the unit of length. So it's dimensionless parameter, which guarantees, if it's small, that we can use perturbation theory, which in classical nonlinear systems is called weak turbulence. So whenever you hear the term weak turbulence, it's all about weakly coupled harmonics. In quantum mechanics, quantum theory, we call it perturbation theory, and use kinetic equation. The same is true for nonlinear classical systems. So basically, when we have such a small parameter, we can use kinetic equation. We can simplify the description. And this parameter becomes progressively smaller down the cascade, meaning that we get an asymptotically accurate description. Finally, a very simple parameter, non-relativistic parameter, in terms of the circulation quantum, the wavelength of Kelvin wave is called Kelvin for briefness, and the sound velocity. So this parameter is typically very small, meaning that at the main scale we can completely forget about the interaction between Kelvin waves and phonons, and also we can forget about the compressibility of the liquid. So the liquid is incompressible. And let me also remind you that the Kolmogorov turbulence of an ideal liquid is all about incompressible regime. Compressibility is irrelevant for Kolmogorov turbulence. Now, the main equation is the so-called Biot-Savart equation. It's just an equation, a classical hydrodynamics without friction. So, what is the origin of this equation? The origin of this equation is the famous Kelvin's theorem of an ideal fluid, which says that the vorticity moves with the local velocity. So basically, the vorticity is being carried by ideal fluid with the local velocity, which immediately tells us how to describe the evolution of vorticity. So our vortex lines are infinitely thin. Remember that parameter, that the interline separation of curvature is curvature radius is much larger than the Healing length, the core radius, meaning that we can represent the lines as just geometric lines. Then what we need to do, we need to calculate the velocity field. And the calculation of the velocity field is equivalent to calculating the magnetic field created by wires which coincide with our vortex lines and the currents being proportional to the circulation quantum. And that's why we have this Biot-Savart expression in the right-hand side. It's just a resolvent for the velocity field, for the instant velocity field. And the left-hand side comes from the Kelvin's theory. Kelvin theory says, once you know the local velocity field at this point will be moving with this local velocity. Now, there is some formalism which I developed in '95. It's basically the same equation written in the Hamiltonian form. So if we have a line which is almost a straight line, the only thing actually we need is single valuedness of the function describing the position of the line in terms of its z coordinate. If this function is single valued, we can introduce actually x and y coordinates in the plane perpendicular to the z-axis. And then, instead of working with x and y coordinates, we can introduce a complex number which consists of x and y coordinates of the vortex line as the function of z. And it turns out, it can easily be checked, that if we write down the energy of the system expressed as the function of the position of all lines, in terms of this variable, we will see that this is a canonical complex variable, so that the equation of motion can be written in the following canonical way, with the Hamiltonian function being expressed like that. Why this is important? It's important because if we want to construct kinetics, Hamiltonian formalism is what we need, because by our experience with quantum mechanics, we know that once we know the canonical variables, we can quantize everything and immediately apply the golden rule. We can immediately describe the kinetics in terms of scattering, of kelvins. We can immediately apply the golden rule, quantum mechanical golden rule, even if the problem is classical. Of course, the Planck's constant will immediately drop out from the answer, but basically a very straightforward way to immediately write, or almost immediately write, the kinetic equation. Okay, now let me explain what is the local induction approximation. Actually, when I was writing the Biot-Savart equation, I didn't tell you that the equation was singular. Maybe I just go one slide back. You see here we have this term which actually diverges when we do the integral. The divergence is only logarithmic, meaning that we can just introduce a cutoff, and this cutoff is nothing than the size of the core. And that's why we get this log as our large parameter, which is I was mentioning, the log of the ratio, because we integrate essentially from the scale, which is the curvature radius, to the scale, which is the core size, and the divergence is only logarithmic. Meaning that the main contribution, at least if we are considering a single line, comes from small distances, and as a result, we can, if we care only about the leading contribution, we can replace this non-local in space Biot-Savart interaction with just local. And this local Hamiltonian will look pretty simple, and this expression, you can immediately see that this expression is nothing but the line length, geometric line length. So in this local induction approximation, the Hamiltonian function is nothing but the length of the curve, meaning that the length of the curve will be conserved, exactly conserved by local induction, within the local induction approximation. And this log, which I was mentioning, this large parameter, can be actually taken out of the integral with the same logarithmic accuracy, because it's a very slow function of everything. So the first approximation in this parameter is just a constant. That's why it's just taken as a constant. So this constant is circulation quantum over this log over 2 pi. The next step is to linearize this dynamics to get Kelvins. And if we linearize, by linearize the Hamiltonian to get the linearized equation of motion, we end up with this equation. Do you recognize it? What is it? The Schrödinger's equation. So it's interesting that actually Lord Kelvin, actually he was Thomson that could discover the Schrödinger's equation. But for some reason, probably he was not using these complex variables. Otherwise, Schrödinger's equation would be called.
But wasn't it known?
I don't know. I have no idea.
So this is a kind of derivation that has, for instance, been used by David Nelson at some point in history. So that goes to my next question. I'm curious. You are basically working out now what is, in effect, a non-relativistic approximation to what is ultimately relativistic theory. And the relativistic theory would be theory in which your vortices, in fact, come around and turn every which way. So you don't have a single valuedness along the plane that you've selected.
We will discuss this. It will be very important.
Okay, very good.
You see, here I'm interested in
no, that's okay. That's okay.
But we will discuss it. It's very interesting and a very good question.
Okay.
So basically, this Schrödinger's equation describes Kelvin waves. So to get an idea what are the Kelvin waves, you just need to use your experience, your intuition about one-dimensional Schrödinger's equation. So they do like that. So they are not like the waves on a string, in which case we would have two polarization, just single polarization, because they are essentially distortion waves. Okay, now we know everything about the Kelvin waves, and let me just mention some conservation laws, because you will see that actually this theory of low temperature superfluid turbulence is all about applying conservation laws and more general symmetries. So the energy conservation, I already mentioned that the energy is just the total vortex line length in the local induction approximation. And it will be important that momentum conservation is really important. I didn't write the expression for the momentum, but just believe me that for a vortex ring, momentum scales like its area. So if ring is very sophisticated, then it will be algebraic area. And this fact will be really important. That angular momentum, if we have a line with Kelvin waves, then the angular momentum is nothing else than the number of kelvins, because a single kelvin carries a quantum of angular momentum, and that's why the total number of kelvins is conserved. It's a very important circumstance in terms of the kinetics that we will see. So there are no processes in which kelvins are created or annihilated as long as we are discussing just a single one. Finally, it turns out, and this just adds some interesting feature to the whole theory, that the local induction approximation is actually an integrable theory. So, meaning that the dynamics, if it's governed only by the local induction approximation, is trivial. We cannot have a cascade, a Kelvin wave cascade, within bare local induction approximation. And it's actually a very interesting, very elegant theory by Hashimoto, who demonstrated that the local induction approximation can be written in such a way that you use internal variables, curvature and torsion, in which case you can introduce a complex field, the absolute value of which is given by curvature, and the phase of which is related to torsion. And in this Hashimoto's representation, the local induction approximation is nothing else than one-dimensional Schrödinger's equation with attractive interaction. And this system is known to be integrable. It's known to have solitons. That's why within local induction approximation there are solitons, called Hashimoto solitons. Just very interesting circumstance, but we should remember that this is only in the local induction limit. So non-local terms break down integrability. And also vortex line reconnections break down this integrability, which will be also very important. So basically, how do we create Kelvin waves? So we understand that if we want just to cascade our energy, which is nothing but the total line length, we need to convert the line length into Kelvin waves. And the natural way to do that is through the reconnection. So it can be accurately shown, because there exists a self-similar solution for the reconnection of two straight lines, that when we do a reconnection, we create a packet of Kelvin waves. So then we can say, okay, then the rest is the piece of cake. We permanently create Kelvin waves. They interact non-linearly, and this gives rise to the Kelvin wave cascade. But the problem is that if we plug in the numbers, if we plug in the rate at which we pump the vortex tangle with Kelvin waves, and if we just estimate, and we estimate the efficiency of this cascade, the fact that the leading term given by local induction approximation doesn't transfer the energy will tell us that the efficiency is not good enough. So we cannot directly accommodate this flux of line length by some purely nonlinear Kelvin wave cascade. Something else should happen. And at this point, we can recall that back in 1955, Feynman, in his famous paper on the vortices in superfluid, suggested a scenario which basically then was accepted by the community, that we don't need any Kelvin waves, and Kelvin waves were not discussed in Feynman's paper at all. We just need a cascade of vortex rings. That's basically the Feynman's idea, that one ring can split into two, and then you continue by further splitting these rings into smaller and smaller ones. So what is wrong with this scenario? Remember, I was telling you that the momentum scales like the area of the vortex ring, and the energy scales like the total line. There is no way we can conserve both the area and the line in this process. So basically, Feynman's scenario cannot be reconciled with the conservation of energy and momentum. Somehow people overlooked this simple fact. We cannot do that. But what we can do self-reconnection. And that actually was my idea, which I proposed in 1995, that if we have a kinky vortex line, then we can do self-reconnection. We will create a ring. As a result of this reconnection, we will create some Kelvin waves. This ring will be reabsorbed. So that's the difference with Feynman's scenario, that this ring will be then quickly reabsorbed by the tangle, also creating some Kelvin waves, and then we can have the same picture at any length scale. So basically, it's a kind of combination of Feynman's idea, but it's not a pure Feynman's idea, because crucial part is played by these Kelvin waves. So basically, it's a synergy between the rings and Kelvin waves. So this self-reconnection supported Kelvin wave cascade. And here is an interesting model frankly, first of all, I was naively simulating this model, seeing the cascade, and only then I realized, with the help of Vladimir Yankov, who told me that there is no way an integrable model can support a cascade. Somehow I overlooked this fact, that I was simulating this model and I was seeing a perfect cascade. So what's wrong? And this model is nothing else by the local, or seems like nothing else than the local induction approximation. And then actually I realized something should be wrong, because frankly I completely forgot about the integrability of local induction approximation. Then I recalled about that. Basically we had an interesting discussion with Yuri Kagan, who invited Yankov just to discuss whether it's possible in principle, and basically the consensus was that if the model is integrable, it's not possible at all. So what do we see here? And here is a clear cascade. And then later on I figured out that actually this model is very non-trivial in the following sense. So it's equivalent to the local induction approximation only if the field is smooth. But with this Hamiltonian, look here we have the square, here we have a square root. With this Hamiltonian we can have finite jumps. And when you do the calculation, when I was doing the calculation, I had a discrete version, a discrete Hamiltonian version of these things. So basically the evolution is as follows. And here they actually come to the question by Zlatka, what if the system is not single-valued? Because in this model everything is single-valued by definition, meaning that if the original field wants to be non-single-valued, it's exactly the moment at which this model develops a jump leading to the breakdown of integrability. So it's a very non-trivial, fully Hamiltonian model. Nothing is done by hand. Everything is done by this model, but this model contains both integrable pieces of evolution and jumps which qualitatively are equivalent to creation of vortex rings. So when we have a jump here, we create a packet, I checked it explicitly, we create a packet of Kelvin waves. It's a Hamiltonian model in which nothing is done by hand. And that's qualitatively the spectrum which you expect. So basically it's a kind of confirmation of this idea of vortex ring to connection scenario. Now, yes? Sure.
So your previous argument is based on a simple, not previous. Yeah, previous. So, yeah, single vortex
yes.
ring.
Was
what happens if everything goes as a bundle?
Oh, it's also a good question. So if the radius of the ring is much larger than interline separation, it doesn't really matter whether it's a ring or a line, because large rings, for all practical purposes, large rings are indistinguishable from the dynamic point of view, kinetic point of view, from just very large lines. So we care only about rings, the radius of which is much smaller than the interline separation. So if you do a simulation and count your rings, please make sure that you actually study the spectrum of the rings rather than the fact that you do have the ring. Because if you have rings with radii on the order of interline separation or larger, it's not what was being discussed here. Here we are discussing rings with progressively smaller radii.
For a single line loop, I agree with this argument that simultaneous conservation of energy and momentum is not possible. I'm not quite sure if everything goes in the bundle.
In the bundle, that's the scenario. That's exactly the scenario, because you see, if you have a ring in a bundle, it will be reabsorbed.
Yes.
That's the point. Yeah. It will be reabsorbed.
So
and that's the crucial step.
Yeah, I'm just trying to understand. If everything goes as a bundle, then cascade process could go.
That's exactly my scenario of 95. So basically you have a synergy between rings and Kelvin waves, because whenever this guy, you see, whenever this guy is emitted or reabsorbed, it pushes the cascade down because it creates shorter Kelvin waves, and these shorter Kelvin waves will lead to creation of smaller rings, and so on and so forth. So these are two sides of one and the same metal, Kelvin waves and rings. Rings create Kelvin waves are responsible for this self-processing. Okay?
Can you clarify what is the bundle and why is it going to be observed?
Let's call it tangle at this moment.
Okay.
The term bundle will be used later. Why it's observed? Just because normally you do a theory of infinitely large tangle, right? So there will be some free path of your vortex ring before it hits some line. Because vortex ring just moves and just hits some line. That's reabsorption.
Why would it be
Why what? But where do you want to take your ring? So you have a ring, it moves, and sooner or later it meets some line.
Okay, so Feynman didn't realize that.
Feynman was thinking that he didn't need that. Feynman was thinking that he starts with just a single ring and the whole thing cascades.
But the important part is that the small rings will continuously be observed.
Yes. In Feynman's case, it was like you continue with a single ring.
Okay, so the important thing is fluctuations of the line.
The important thing is that the guy gets reabsorbed, in which case you don't care about the momentum of a single ring. You only care the ring exchanges momentum. Actually, it exchanges everything, because once it's reabsorbed, it disappears.
In a sense, it's a many-body process.
Right. It's a
many rings,
exactly.
constantly
so
connecting,
in
reconnecting.
Rings, it's a many-body process. So the guys appear and disappear, and once they appear and disappear, the other side of the medal are Kelvin waves, generated by this self-crossing and reabsorption. Okay? But actually, this cascade will take only about 1 decade, because you see, if you go down to the cascade, the nonlinear terms become important. So this is just picture. So in a computer, you can just simulate local induction approximation, but in a real life, you can estimate that this cascade will take maximum just about 1 decade. And then the nonlinear terms will take over. So the most important part will still be this pure Kelvin cascade, which is supported purely by non-linearity. And we developed this theory with Jane Kozik in 2003 using this small parameter, which I already mentioned, the amplitude over the wavelength. And here are the most important ingredients. Remarkably enough, we don't need to go into details, because we can just use only dimensional estimates and some general considerations. So what's important for us? Kelvin is a good elementary excitation because just this amplitude is small. The number of kelvins is conserved due to the rotational invariance. I was already mentioned that. It's the conservation of angular momentum. And then, to get the Kelvin Hamiltonian, we just expand our Hamiltonian, which I was writing when I was discussing the Biot-Savart equation, in terms of this small parameter. So this small parameter allows us to expand the Hamiltonian and to produce just the series of vertices. Actually, we need just the first 2 of them, this one and that one. You can ask a question, why do we need 2 rather than 1? This is because kinematically, in 1D, this vertex doesn't lead to any non-trivial kinetics. Because once the energy and momentum is conserved, you cannot just scatter onto particles non-trivial. It's a coherent process. So the bottom line is this 3 Kelvin elastic scattering. It's just the minimal possible process, consistent with the conservation of the total number of particles and one-dimensionality of the problem. And there is a bare 3 Kelvin process which comes from the Hamiltonian in the second order 3 Kelvin vortex, which is generated by the 2 Kelvin scattering. Then you write down the kinetic equation, and then you do a standard dimensional analysis with one important ingredient. So whenever we have these weak turbulent or perturbative kinetics, and a crucial question is whether this kinetics is local in the momentum space, meaning that the most relevant collisions involve kelvins of kelvins with the energies of the same order. So it's not necessarily the case. In some systems we have local kinetics, in some systems we don't. For example, if you have a system with Bose-Einstein condensate, we know that the leading process in terms of phonons will be so-called three-wave process, where we have, and this, in terms of number of waves, this will be the six-wave process, when we have the number of waves is the number of ends in a diagram like that. So on top of Bose-Einstein condensate, our normal process would involve, say, two phonons creating one, or just one phonon decaying into two, because the fourth particle is condensate. Condensate plays the role of external field. So once again we have a process which can look like local but three-wave process, or the process which is a four-wave or two-particle which is non-local. So generally speaking, a priori, locality would be as probable as non-locality. And under the assumption of locality, we would get this spectrum for the Kelvin wave occupation numbers, which can be also translated into the spectrum of amplitudes at a given wave vector. And numerically, we did check back in 2005 from the first principles by simulation of the Biot-Savart equation that indeed we have this spectrum with great accuracy. We developed a very efficient scheme reminiscent of three chords, which used in astrophysics because the system features no local in space interaction, but somehow you can render it as efficient as local one. By in our case, the trick was that we were addressing long distances only rarely, and for some just historical reason, a good starting point was this spectrum k to the minus 3, which is pretty close actually to the spectrum of the cascade supported by the self-process after a logarithmic correction. Recently, and basically this fact in the community, in the super fluid turbulence community, this spectrum was considered to be well established until very recently. Lvov and Nazarenko, essentially 1 year ago, attacked us, saying, just attack the spectrum, right? Saying that actually we were wrong, that actually the kinetics is non-local, and once it's non-local, the correct spectrum should be 11/3 rather than 17/5. Just to make the long story short, I will show you a new simulation on a laptop. It's an overnight simulation on a laptop which we did recently, showing how this hypothetically correct Lvov-Nazarenko spectrum actually is being destroyed by evolution into our 17/5. So it's a smoking gun, first principles evidence that the Lvov-Nazarenko spectrum is wrong, or at least irrelevant to this problem, but this spectrum is correct. And actually a bit earlier, the reason why we had to do this simulation is because somehow the community was not able to accept our very simple argument, which I'm going to give. Because once we saw the Lvov-Nazarenko paper, we started thinking, why on Earth we actually do have this locality, is it a coincidence or not? And we arrived at a very interesting understanding that actually this spectrum, a priori we were thinking locality is as probable as non-locality. And after thinking a little bit, we realized that actually the locality of this spectrum first can be rigorously proven, and second, it's quite not trivial. So here is the proof of the locality. It turns out that the locality is totally due to geometric symmetries of the problem. which are actually pretty close to the symmetries which Leo Radzikowski was mentioning in terms of the smectic liquid crystals. So the geometric symmetry is basically the fact that our field, which we are studying, is of geometric origin. And clearly, the vortex line is a purely geometric field, just a position of some points in space. So what do we have from these geometric symmetries? From these geometric symmetries, we have the following statement, that even if we have a non-left source, suppose our spectrum is non-long, but in which case our collision term in kinetic equation, this is the kinetic equation, should somehow depend on the local in space geometric properties of our field. It's a general expression for non-local kinetics, which is sensitive to some properties of our field, which is nothing special. But then, if we will take geometric symmetries into account, we will understand that actually the field cannot be sensitive to the amplitude of the field, because the amplitude of this field W is nothing else than the absolute position of our line in space. So if we change this amplitude, it's equivalent to just shifting the line in the perpendicular, in the transverse direction. But shifting this line changes nothing. The system remains the same. The implication actually of this symmetry is that the condensate of Kelvins completely decouples from the kinetics. Nothing is coupled to the condensate of Kelvins. And actually, this expression is just the condensate. It doesn't evolve in time. The amplitude of the condensate doesn't evolve in time because it's just the position of the line. So the amplitude is excluded, but the angle should be also excluded. The angle should be also excluded just because if we tilt the line locally, we cannot couple to it. So actually the mistake by Vok and Nazarenko was the following. Instead of considering the original model, they were considering what they were calling simplified model with some truncations and stuff. A question?
No.
With some truncations and stuff. And by doing this simplifications, they actually violated this tilt symmetry. So their model was not featuring the tilt symmetry, and in their case, they were coupled to the angle of the line, which is absolutely not physical. And it's very interesting why they were so confident that they did it right, because in addition to that model, they tried to derive the kinetic equation after us, and they observed that they have some extra terms in addition to ours, and they say, okay, due to these terms, we see that they didn't actually say that due to this, and they were just saying that, okay, here are the different terms, and with these terms we see that the kinetics is non-local. But it's basically the same scenario. Once you have some extra terms which come by mistake, you actually violate this tilt symmetry. So basically the conclusion is that the Vok-Nazarenko spectrum is the spectrum of errors and uncontrollable approximations. In both cases, we just... but it's very interesting, because once you see the spectrum, you understand that something is going wrong. So it's not just arbitrary. It's an indication that you violated the angle, just violated the tilt symmetry. So moreover, it's a generic spectrum. Whenever you have something which is consistent with just analysis of dimensions but doesn't respect this tilt symmetry, you generically get the Vok-Nazarenko spectrum. Okay. That's basically, but still we have to prove the locality theorem, because so far we just demonstrated that we are coupled to the curvature. It's not yet the locality proof. So now comes the locality theorem. We start with the collision term corresponding to this spectrum, and we want to prove that it's local. we want to prove it by contradiction, and we suppose that the opposite is true. So that this spectrum is non-local, in which case we are supposed to be coupled to the curvature, only to the curvature, not to the amplitude, not to the angle. And then, the only thing we need to check is whether the curvature comes from the long waves or from the short waves, because the only consistent scenario in this case is that the curvature should come from the long waves. Otherwise, we are in a contradiction with the original assumption that we interact with long wave part of the field. And then, just explicitly inspecting the expression for the curvature, we see that the curvature actually with this spectrum comes from the short waves, meaning that the non-local assumption, the assumption of non-locality was wrong. It's not a contradiction. So that's the end of this locality issue, and that's the overall picture of the cascade in the random tangle. So we start with pumping the tangle with Kelvin waves. Then we have this self-crossing assisted scenario. Interestingly enough, in the year of 2000, there were numeric simulations based on, by Tsubota groups, by Makoto Tsubota groups, based on local induction approximation. So with these simulations, only this scenario could take place, because just nonlinear scenario could not. It was based on the integrable model. And they did observe rings, but somehow they didn't study in detail. The scenario. So they were observing rings, and they were saying in their paper, oh, we observe the Feynman's cascade because we do see the production of the rings. And this is the experiment in which people saw that when you go to low enough temperature, the relaxation time gets temperature independent, meaning that there is some sort of a cascade. The evidence is still circumstantial. You just understand that there is some cascade, but you don't understand the details. Now comes the pure cascade with no reconnections, which we just discussed, and there were numeric simulations. In addition to ours, there were simulations by other groups who also saw this cascade. And finally, if the temperature is 0, the whole thing is cut off by the emission of sound, as was proposed by Weinen in the year 2000. So let's just discuss the more non-trivial case of Richardson-Kolmogorov regime. So what's special about this regime? Once again, just familiar names, Vlok and Nazarenko and their student. They suggested and put forward an idea of bottleneck. What they did at that time, it was earlier than this non-locality issue, so that at that time they were very happy with our spectrum, and they were trying just to do the following. They were trying to directly connect the Kolmogorov regime with our pure Kelvin wave cascade, just ignoring this self-crossing regime. Just for some reason, they were trying to connect the two, and no wonder they observed that they cannot connect. Remember, even in a random tangle, the pure Kelvin wave cascade was not able to accommodate all the energy flux. So this problem, this bottleneck, was sort of their arbitrariness, because somehow they were trying to arbitrarily require that there is a direct crossover from Kolmogorov to pure Kelvin wave regime. And the way out that which they suggested was kind of non-trivial bottleneck, accumulation of energy, just creation of some classical microscopic motion, classical motion at these intermediate scales with some temperature and stuff. And as a result, their main prediction was that the total line length should be increased by orders of magnitude, like 1,000. So the experiment was supposed to see that if you go to low temperature, you see that the total line length gets larger by a factor of at least 1,000. What they missed actually was the fact that there are reconnections which were playing a crucial role in the random technique, and the reconnections are supposed to play the role here. And that was basically our idea with Kozik after we've seen this paper by Lvov, Nazarenko, and Rudenko, that somehow we need to develop an accurate theory of these crossover, which should be really based on reconnections. Because reconnection is something unavoidable if you have just a motion like that. And that's the explanation why reconnections are unavoidable. So if you go to smaller and smaller wavelength, remember there is a self-induced component of motion which comes just from the curvature. When you go to the scales at which this self-induced motion can compete with the induced velocity, with the velocity induced by these polarized eddies, polarized bundles, then the line will ignore its neighbors and it will be moving on its own. And when the line starts moving on its own, it can naturally reconnect with the other line. But somehow it's the bundle which becomes moving on its own, because you can easily figure out by just studying the competition between the self-induced motion and induced motion that because of this large parameter lambda, the self-induced motion becomes dominant at the scale of distance which is larger than interline separation. Not dramatically larger, because we have just a square root of 10, so it's basically almost the same order. But in the theoretical limit of very large lambda, there is a large parameter which controls this fact. That first, the bundle, the whole bundle, is driven by the curvature. What happens then, as a result, we are supposed to have reconnection of the whole bundles, because the whole bundles just move. The motion of the whole bundle is governed by the local induction approximation. So that's what we are supposed to see at these length scales. And interestingly enough, a simulation of that type was done recently by Carlo Barelli and collaborators. They explicitly demonstrated that if you have two bundles, they indeed reconnect as if it's just one thick vortex line. So it's consistent with our idea. And when they do that, they generate Kelvin waves. And Kelvin waves is what we need. So I will not be going in all the details of this crossover between Kolmogorov regime and Kelvin wave regime. I just mentioned what's in between. So we just discussed these bundles. Then the next inertial range is due to the reconnections of adjacent lines. And finally, we end up with what we are already familiar with, self-crossings, and then just pure nonlinear Kelvin wave picture. And that's basically, so, and this, given that lambda, this large parameter, is on the order 10, the whole range of the crossover takes about 1 decade in terms of the wavelength scales. So that's basically the picture of what we see in terms of the spectrum of Kelvin waves. So how about the experiment? Turning to the experiment, which was done at different temperatures, it's interesting to know that if temperature is small but finite, there will be a cutoff, not due to the emission of phonons, but just due to the friction against the normal component. And here is the friction coefficient, which describes the dissipation of the Kelvin waves due to the normal component. It's a very sharp power of temperature, so this guy gets very small pretty soon. And then we can figure out that as a function of alpha, because the only crucial quantity is alpha, as a function of alpha we can scan the whole cascade. We can see how the line length depends on the temperature. So basically that's the expression for the total line length as a function of the cutoff, which depends on temperature only through this coefficient alpha. And if we go to lower temperatures, and we know how alpha depends on temperature, we will be just seeing that our cutoff moves and eventually reaches the scale at which we are supposed to emit the photons. And then we can compare with the experiment. So these points are the experiment data. Just this is a curve which has a fit. So please don't think that basically there are no fitting parameters. There are lots of fitting parameters for each range, but please note that we are talking of logarithmic units, meaning that our alpha actually changes by orders, by 3 orders of magnitude, while the only parameters which we have are order unity. So we fit a very non-trivial curve which spans over 3 decades by just few parameters of order unity, and we reproduce all the qualitative features of this quite a non-trivial curve, which is the total line length as a function of friction coefficient. And from this fit we can extract just the details of this Kelvin wave spectrum. So basically that's all about the superfluid turbulence per se. And there is yet another topic which I believe just is quite interesting. It's vortex Forman Hamiltonian. So if you are interested, I can continue with vortex Forman Hamiltonian.
Those one is interested, Vitaly.
Yes.
So,
Okay. Let's do this. Let's now discuss. So I was telling you that at 0 temperature, the cutoff.
Would it be appropriate to maybe ask a couple of questions about the previous part?
Yes.
Okay, so I wanted to ask you a question about something that you discussed in the early part of your talk. You talked about these very nice experiments where you have a rotating container of helium which is then brought to abrupt stop, and how they were looking for the length of lines in 2 different directions, along and perpendicular to the original axis of rotation. Was there a significant difference?
It's a good question. Actually, I don't remember the details. But if it would be something, they would report it.
And they kind of did not really mention it.
I don't remember anything about it. A significant difference in just isotropy. Because normally you see during the initial stage you can have something, but they are interested in really in well.
At long time there was no big difference.
In a well-developed turbulence. So they are not interested in this initial spin down when you're supposed to see something.
You may suspect why I'm asking, because as you know, this picture of proliferation of loops can also be used in equilibrium. People have proposed is the mechanism of how you actually lose superfluidity.
Oh yeah, but in the equilibrium, you see, it's not easy. With ions in equilibrium, it will be difficult, I believe, because you will have a significant amount of normal component.
No, I understand. But I'm saying what some people, like me, have suggested, that if this is really the mechanism of the transition without rotation, that at finite rotation, they would in fact be 2 true phase transitions. There would be formation of lattice of these vortices at very low temperatures, which people, of course, have seen in helium. But there also would be an intermediate transition, where in presence of rotation-induced vortex lines, the loops, the very ramified rings of the type you described, blow up. And so this, as far as I know, has never been really seen.
And actually, I respectfully disagree with you, because somehow I don't feel that there will be 2 transitions. Because once you melt, are we talking of melting of the lattice?
Yes, indeed. So
once the lattice is not there, I don't see any qualitative property which could be associated with the second phase transition. Because you see, the vortex lattice is gone. So what's the qualitative property which is there? We can discuss it. It's a very interesting question.
No, we can go ahead there. So
Because somehow I don't have an answer. But
Okay.
It's an interesting question.
Thank
We can
you.
discuss.
Thank you.
Well, let's talk of vortex Phonon Hamiltonian. Maybe we can say it's very simple just to write a vortex, say Kelvin Phonon Hamiltonian. Kelvins are harmonic modes, phonons are harmonic modes. So it's not supposed to be a big deal. Naively, we just take the energy, the interaction energy, just plug the canonical variables, and that's it. That's what people were doing. And it turns out that the Hamiltonian which they were deriving was not complete. So the subtle issue is the following. And this subtle issue actually is very relevant to yet another interesting observation. So if you ever studied, all of us I believe, at some point studied Koster-Stauer's phase transition, Koster-Stauer's theory, and there is something really strange in the Koster-Stauer's theory. So from the very beginning, you decompose the phase field into the part which absorbs all the topological defects, all the vortices. Doesn't matter whether we are in 2D or in 3D for this decomposition, but if we are talking of Koster-Stauer's theory, we are talking of 2D, then we impose the constraint. That's basically the idea of this decomposition, that this field phi naught, which absorbs all the defects, obeys the Laplace equation, because in this case, statistically, topological defects get independent of this regular phase, and normally people would say that this regular phase describes phonons, and this phase describes vortices. So I have at least two objections about this picture. First of all, how about causality? Because we know that the signal and fluid propagates with the sound of velocity, and somehow this field reacts immediately to any displacement of the defect. Yet another, so this is a dynamical objection against calling this guy a field of phonons. Then there is a statistical objection coming from the Koster-Stauer's theory. So these two fields are known to be statistically independent. You just have an action for this field decoupled from the action of vortex pairs. We all know that Koster-Stauer is all about the Coulomb gas of these pairs. Then we believe, it's just the main paradigm, that these vortex pairs renormalize the superfluid stiffness. The superfluid stiffness is the property of this field. So somehow, on one hand, the vortex pairs are independent, statistically independent of this field, and they are supposed to renormalize its stiffness. Sounds controversial. More than that, if we would like to calculate, say, single particle density matrix, we will see that there are two independent contributions. Independent because the two fields are independent. There are two independent contributions to the long-range behavior of the density matrix of the same order, coming from this field, from the defects, and from this regular field. Moreover, both contributions would be sensitive, which is very non-physical, to the microscopic value of the superfluid stiffness, to the background value of the superfluid stiffness, which is supposed to be not absorbable from large distances. Moreover, and that was called a conspiracy between vortices and phonons, what wrote phonons, is that this dependence on the background superfluid stiffness disappears when you multiply two exponentials, when you sum up two exponents, each of which coming from two mathematically independent fields. So some conspiracy between mathematically independent objects. So what's the way out? At this point, we start to suspect that actually our idea that this field represents phonons is correct only in the absence of topological defects. And when we add topological defects, somehow this field of phonons should be corrected. So something contained in this field of defects should be actually attributed to phonons. speaking physically, it means that this field is not a canonical variable in the Hamiltonian.
Boris,
Yes?
a question about the first issue you brought up about the dynamics, the causality. That in principle has no bearing whatsoever on the transition because it's finite temperature and the thermodynamics.
I was not saying that the theory is wrong. I was saying that something is enigmatic because mathematically these guys are indeed statistically independent. Mathematically the final answer is absolutely physical. It doesn't contain any memory of the background stiffness. So somehow I was just saying that we do not understand the origin of this conspiracy between two statistically independent fields when you calculate the long-range correlations. So I was not saying at all that the Kosterlitz-Thouless theory is wrong. I was saying that there is something which we would like to understand. And let me put it this way. There should be some way of reformulating Kosterlitz-Thouless theory in a purely RG sense, in such a way that small vortices do not contribute at all to long-range correlations. Because in this picture, small vortices do contribute to long-range correlations, which is not physical. It's mathematically correct, but not physical. You see, somehow we want these small objects to be invisible from large distances. And if we use this parameterization, they are visible in the single particle world. So I really want to reformulate Kosterlitz. I'm not saying that it's wrong.
So why can't we think of it as Coulomb gas, but then with Maxwell electrodynamics in addition? Not just
you
the
can,
static.
and that's exactly the representation. But in this case, if you want to calculate how your single particle matrix decays, you have to take care of two contributions to the decay of single particle density matrix. One coming from this field and another one coming from dipoles, from vortices. You have to explicitly calculate how your vortices screen or just lead to the decay of single particle instead of just working with one field, with phons. Physically, you want to work with just phons, right? Somehow people are trying to circumvent this. Yes? Okay?
Well, I agree that small objects is invisible at large scale,
Yes.
but yet that can affect dielectric constant.
Exactly. And that's what we want to understand, because somehow these guys are supposed to affect the dielectric constant while being statistically independent of this field. So that's exactly the issue, because the dielectric constant is equivalent to superfluid stiffness. And the superfluid stiffness is the property of what we call the Forman field. But somehow the stiffness of this field comes from the background. It's not renormalized. So somehow we are dealing with the field, the stiffness of which is not sensitive to the renormalization of the electric constant. That's the conspiracy. Okay? And my point is that actually this is not the Forman field. To put it differently, this is not the field which is sensitive to the dielectric function. Okay? As I said, the proper decomposition would be that instead of this field, we actually take the long-range part of this field and attribute it to this Forman field. But it will, yet another statement is that this will happen automatically if we introduce the canonical variables, dynamical canonical. So the beauty of all this stuff is that if we do dynamics canonically, starting from Lagrangian, we would automatically get such a representation that would be different from this one. So if we do canonical variables, we will automatically get such a picture in which the long-range part of the field of vortex dipoles or Kelvin waves will be automatically included into the Forman fields. Okay? And let me show how we arrive at this picture. So basically I'm saying that there are two equivalent formulations of the Kosterlitz-Thouless theory. In one formulation we have independent Coulomb charges which do not talk to some supplementary, non-physical, regular field, and then we have to calculate separately the contribution of these guys to the single particle density matrix, contribution of these guys, we have to multiply through exponentials to see how the background stiffness drops out, or we can reformulate the theory in such a way that the vortex pairs are directly coupled to the phonon field, and we explicitly see how this coupling leads to the renormalization of superfluid stiffness. Two formulations are mathematically equivalent. The bottom line is the same. But the second formulation is very intuitive. You explicitly see how vortex pairs are coupled to the phonon field. That's my point. Otherwise, mathematically, the bottom line is the same. But dynamically, there is no way around. Because dynamically, we need canonical variables to write down the Hamiltonian. Statistically, we can do both ways. It's the matter of taste. Dynamically, if we want to construct the Hamiltonian, there is no choice. We have to go with the canonical variables. That's the point. So, how? What's the subtlety? I already discussed it. I already gave you an idea. And in terms of the Lagrangian, this subtlety comes from these terms. So if we introduce this decomposition as a zeroth approximation, and if we ignore all the interactions, then both fields are canonical. By both fields, I mean, excuse me. So this field and this field are canonical as long as we ignore all the terms of the Lagrangian which are responsible for the coupling. That's basically the subtlety. And there is no wonder that basically the Lagrangian for the field phi naught will immediately yield the Biot-Savart equation, which we already discussed. So the Biot-Savart equation would immediately follow, because the absence of interaction means that our approximation is the approximation of incompressible fluid, no coupling to phonons. But if we take into account this term, we will see that in addition to the direct interaction, direct term which gives the energy of interaction, there is some term which does not give the energy. So this term produces no energy if we write down the energy out of this Lagrangian. But what does this term do? It actually says that our original canonical variables are no longer canonical, up to some small correction coming from this term, because the interaction is small in the long way. So the method of solving this problem is just standard perturbative method. We just need to perturbatively fix the problem with canonicity. We need to perturbatively take into account this term, and it turns out, as I was already mentioned physically, that if we do it purely mathematically, the bottom line will be that this long-range part of the field of distortions on the vortex line should be attributed to phonons. So the variables, the Kelvin variables, remain canonical, but the phonon variables should be correct. And after we do that, we generate some extra interaction which comes not from directly from the interaction energy, but it comes from the bilinear part of the non-interacting Hamiltonian by this correction of original variables to the canonical ones. And this is the series of interactions which we get in addition to this direct interaction, which normally was considered by people who were trying to use the Hamiltonian formulas. So basically, what do we see here? So this wavy line is a phonon, and the expansion in terms of the phonons is in terms of the non-relativistic parameter, meaning that the 2-phonon, 3-phonon processes are progressively suppressed by this parameter, and we also have 1, 2, 3, and so on Kelvin processes. They are also progressively suppressed by this non-relativistic parameter. And with this Hamiltonian, we can do just different stuff. First of all, we can accurately calculate the radiation of sound by this pure Kelvin wave cascade, just obtain the cutoff accurate relations and stuff. So this is basically the process, 2 Kelvins with almost equal but opposite, almost equal in terms of the atomic but opposite momenta collide and produce a phonon. That's the main process, kinetic process, which leads to the radiation of sound then we can resolve some controversies. In literature, there are controversies concerning just these vortex-phonon interaction. So, if we discuss the scattering, in literature people were discussing the scattering of phonons from the vortex lines, which, by the way, is important for this friction between the normal component and vortices. There are different results. The result obtained by Pitaevsky and by Sonin, one and the same one, also by Erdansky, and then the result by Fetter, which is different from the result by Sonin. When I asked Sandy Fetter, what do you think about that? I'm just giving this presentation at some conference. Fetter immediately said, okay, you know what, whenever there was a controversy between me and Eduard Sonin, normally Eduard was always right, and I was young and it was so it's a very constructive approach. But there are other approaches like the one by Ao, who keeps saying that no, just Sonin is wrong and stuff. So what's the resolution of the controversy? So you see, in addition to this direct interaction between the phonon and vortex line, which is equivalent to the vortex with fixed position, there is this interesting process which comes from this non-trivial term which is generated by linear terms when we correct the variables due to non-canonicity. So this extra term, speaking physically, this extra term describes the virtual recoil of the vortex core. And basically this recoil was emphasized by people who were just, the method of these people was very consistent. They were not using the Hamiltonian formalism, they were just solving the equation of motion. And basically the recoil was automatically taken account by the equation of motion. The Hamiltonian formalism is simpler, but as we saw, it's not the problem of formalism, it's the problem of properly writing down the Hamiltonian. So some terms will like it. And if we just take to account these terms, we see that the recoil, the fact that the vortex core is not fixed, is not nailed in the liquid, but can actually move, it's expressed by this second order process. So these terms are one and the same order. And if we combine them, we get exactly the result by Sonin and Erdansky. There is yet another result by Fetter, which we found to be wrong. Is the result of inelastic scattering. So, because Fetter was taking into account only this vortex once again, basically as if the core just there were no recoil, and if we do it properly, just the answer will be different. So basically,
how big is the correction due to your extra term? How big is the difference?
The two terms are of the same order. That's the point. So the number is different. So it's not like a different scale, but the number turns out to be different. They are of the same order. And the dependence will be different.
You also find that the Jordansky force is wrong or not?
Oh, it's a good question. In principle, with this Hamiltonian, we could check, directly calculate the Jordansky force by some method. And so far, just Kozik had no time. And basically, it should be a very, just like a few day work. Just say to write down the Green's function and to check what's the Jordansky force. It's a very interesting project. We keep it in mind, but so far, Zhenya was really busy with other stuff because, as I said, it's just something which we do for fun out of
If you say that the Jordansky force is wrong, I will disagree with you.
No, the Jordansky force is correct because the people who are saying that it's wrong, they are in this line.
Yes. These are exactly those people.
So the project is just to derive the Jordansky force, and you see we have no reason. We have no reason to suspect Jordansky or Sonin or Pitaevsky. We do have a reason to suspect those guys.
Yes, but those say wrong.
So yes, it's a very good question. So you can use this Hamiltonian to derive the Jordansky force in a very industrial manner, like using the standard field theoretical approach. Once you have the Hamiltonian, you're supposed to derive everything. So the Hamiltonian is there. So if you have time, just go. So basically, this is the list of main results. Just take home results. So absence of Feynman's vortex ring cascade, suppression of Kelvin kinetics by integrability of local induction limit, self-crossing driven Kelvin wave cascade, detailed theory of Kelvin wave cascade in the weak turbulence regime, then an interesting proof of locality. I believe this physics can be generalized to other systems because it's all about general geometric symmetries, and maybe this type of proof of locality or some other properties can be used, I don't know, liquid crystals or some other systems where the degrees of freedom, membrane or the degrees of freedom are purely geometrical nature. Then we proposed a theory of the crossover between Richardson, Kolmogorov, and Kelvin wave cascades, and just a couple of interesting results about the vortex-Coulomb interaction, starting from complete Hamiltonian theory of sound radiation by superfluid turbulence and resolution of some controversies and paradoxes of vortex-Coulomb interaction. Thank you. Questions?
This is a very vague and general question, but suppose if your vortex contains some bound quasi-particle state, how would that affect all this your picture?
Okay, let me think a little bit, because you know what? I would say that to the first approximation, it depends whether its particle, say, is massive. For example, you have something bound, say iron bound by a vortex line. So if it's large enough compared to the vortex size, maybe it can affect. But if you have something small, I don't see just any reason to believe. Normally, if you change the structure of the vortex core, you do see some effect. Naively, I would say that if it's something small comparable to just a single atom, I wouldn't expect a big difference.
I'm thinking more of along the lines of like the Jan-Caroli metricon kind of bound state of the vortex running along the vortex line. Is that going to really affect?
So, just we need to do some estimates. For example, if you get some extra energy contribution, comparable in terms of energetics to the energies involved in this local induction approximation, of course you will immediately change the picture of this motion. The point is that the energetics should be comparable to that of the vortex line. That's how I would do an estimate. I'm not aware of some just works or some experiments which would just try to address this issue.
More questions?
So about the last part of the talk, so somehow I would expect by universality that if you treat the coupling between vortices and phonons correctly, I mean, just as you say, it wouldn't really ruin the costless Talos transition. But on the other hand, no, it wouldn't do anything, right?
Oh, yes,
I mean,
yes.
by universality.
Yes.
But on the other hand, the dynamic universality class might depend on how you actually do this. I mean, did you think of that, or I mean, because normally the dynamic critical exponent is c equals 2 at KT transition. So that might be another thing to actually think about.
Because you know what? Somehow people, when they got to this Talos, people were sitting, say, on between two chairs. Because on one hand, they were treating these pairs like independent. But after that, they were saying, okay, but we are not going to do all the theory, say, from the microscopic scale. We will just use the trick of the electric function, which Masahito mentioned. So instead of just explicitly doing everything, calculating everything, they say, okay, let's calculate the response, say, to the twisted boundary condition, or just like the electric function is found the same. Let's measure the effect of a single pair on a superfluid stiffness of DC curve. When they measure that, then they rewrite the whole theory from scratch. They say, okay, then let's just erase everything. Let's recall. Let's forget, about these small vortices. It's doing by hand. since we know their contribution to the static response, to the dielectric function, or just to the superluminous stiffness, it's one and the same. Let's just rewrite the phonon part. Taking into account, let's simultaneously remove these vortices and rewrite the phonon part. You see, it's a kind of taking into account this second language without explicitly writing the coupling between the two fields, by just measuring the response. So in a sense, people were doing right things without just quite understanding why you have that. They were doing the right things in terms of RG treatment of the problem.
That's a consistent approach.
Absolutely.
Yes.
Absolutely. Absolutely.
Is there any situation where if we don't understand these relations precisely, we make mistakes?
Of course, it's dynamics. It's all about mistakes.
Yes.
So this vortex phonon coupling term, when you make the standard duality transformations, what does it look like?
Which type of duality transformation?
The Villan. So
it's a good question. Somehow I don't see the answer.
Isn't it just a vector potential?
Well, this is a dynamical.
But he says it's part of the Hamiltonian, right?
Well, so are you talking about the quantum problem, or are you talking about finite temperature phase transition?
I guess it would certainly affect the quantum.
Because normally I'm familiar with duality transformation in which we have only vortices and nothing else. Here we have phonons and I don't.
No, but phonons, they don't do anything. I mean, it would just be some renormalized effective action.
If you integrate
if you talk about quantum transition.
Because you see, normally phonons are integrated out when we are talking about duality transformation.
They don't do anything. They just renormalize parameters of the Villain action.
Yeah, I mean, one thing you could say in the duality transformation, I mean, if you start from an XY model, you have to make the Villain approximation to get Gaussian integrals to do the final, to get the Coulomb propagator in there. So one way of viewing it is whether there's a difference between the Villain and the XY. And there is no difference in terms of universality. I mean, we know that, again, I mean, that would go against what we know about universality. But on the other hand, it has a huge effect on everything else. Like, for example, TC is shifted by 50%.
The shift of TC, you see, it's not a universal property, it's microscopic
Exactly.
property. So basically, maybe it's...
So this is actually a very crude thing to do that. I mean, this is actually... The Villain approximation, if you call it an approximation, is a really crude approximation. But by universality, it captures the phase transition.
It's probably crude at the microscopic scale, but then you go to a larger scale and you see that this interaction gets irrelevant. Because you see, it's all relevant for dynamic problems, because dynamic problem, you deal with something non-equilibrium, with something which will disappear after that. So it's relevant for relaxation. But in terms of the universality class of phase transition, these are some irrelevant operators which will be absorbed into particular values of TC and stuff.
But so that's one form of duality, to just use Villain approximation. The other form of duality is to think of vortices as particles in some space-time, you say. Then you can write, you can think of them as world lines with well-defined cores. And then that would be slightly numerically more realistic. But these terms would then just be corrections to the effective interactions.
Maybe like a gauge field or something like that.
No, they would not be like a gauge field. No, they are phonons.
Yeah, they are phonons, yes.
The your Biot-Savart interaction is the gauge field.
Integrated out.
Integrated out, exactly. So that can be represented as a gauge field. These are phonons.
The gauge field fluctuations would actually rule in the KT transition.
No. Yes. So okay. So okay.
As I say to the students, it will be your homework.
So can I just make a very quick comment? So yes, you are right. So fluctuations in electromagnetic gauge field in, say, a superconductor would ruin a KT transition. So you are correct. On the other hand, Biot-Savart interactions that he described can be viewed as being caused by dual gauge field.
Right.
And the dual gauge field is not electromagnetic gauge field, but it's actually precisely the gauge field that gives you a Kostelik-Towers transition. So that's what I mean. So in a dual description, phonons would not interfere in general with changing the Biot-Savart part.
Right,
Because they don't see the vortex charge. They are density fluctuation.
More questions? Please the same speaker again.
You see, if you take dual gauge